In this video, I'm going to talk about molarity-molarity stoichiometry problem. So molarity-molarity stoichiometry is essentially a combination of stoichiometry questions and molarity questions. And up until this point, we have used stoichiometry with respect to moles and mass. But I could hide the number of moles reacting in an equation by giving you the molarity. Now recall from previously, molarity is basically a unit that we use to describe concentration, the concentration of a particular solution. Okay, so we have two units to describe that. It can be molarity, which is just a big M, or moles per liters. These two units are exactly the same, so we can use them interchangeably. And basically the general consensus here is whenever you see the big M unit, just convert it into moles per liters. It will save you quite a lot of time and to avoid confusion later on. And essentially, very similar to the mass stoichiometry questions that we talked about in the last video, here is we basically have to deal with and add a step in addition to all the other key steps that we have been talking about, which are balancing the chemical equation, coming up with mole ratios, as well as putting the initial amount into the BCA table. So the added step here is basically convert everything to moles, which we have learned previously in our mass stoichiometry video. And let's go over an example here together. What volume of 0.556 molar HCl has enough hydrochloric acid to combine exactly with 24.5 milliliter of aqueous sodium hydroxide with a concentration of 0.458 molar? So step number one, write the balanced equation. So here I know that I have an acid reacting with a base, which is a very typical neutralization reaction. So I should have a salt as my product as well as water. So in this case, my salt is NaCl. And step number two is to find the mole ratio from the balanced equation. So from this equation, I know that the ratio between sodium hydroxide and hydrochloric acid is 1:1. Now, next step here is I couldn't directly put the information given to me from the question into our BCA table, because all the values are not given in moles. So I have to convert basically molarity to moles. So again, we know the number of moles. We should be able to calculate the number of moles of NaOH from the volume of the solution as well as the concentration of the solution. Because we know that from previous class, we learned that to calculate the concentration of a solution, we use the number of moles of the solute divided by the total volume of the solution. Okay, so here 24.5 milliliter is the solution volume. And then I have to convert it from milliliters to liters first, because I need to multiply by the molarity, which is in moles per liter. Okay, so multiply that by 0.458 moles per liter, and I should get 0.0112 mole NaOH, the number of moles of my solute inside the solution. And then, since the information that I need right now, the initial amount is in moles, I can put it in my BCA table now. So as you can see, for NaOH, my initial amount should be 0.0112 moles. And I know that at the end of the reaction, all of them has to be gone based on the question. So the change here should be minus 0.0112, and that should give me 0 mole of NaOH. And as for HCl, I don't know what the initial amount is, so I would just put an X there as my unknown, and my change should be minus X. The reason why the change has to be minus X is because of the keyword enough and combine exactly. So I know that from these two keywords, I know that HCl and NaOH, these two reagents, they have just the right amount to react completely with each other to form the products. So again, afterwards, I should have 0 mole of HCl. So what does that tell you from this BCA table? Well, it tells us that in order to calculate the number of moles of HCl to begin with, I could calculate, basically, I can use the number of moles of NaOH to calculate that information. And the conversion factor that I need here will be the mole ratio between NaOH and HCl. So this is what I did here. So 0.112 moles of NaOH, multiply that by 1 mole of HCl over 1 mole of NaOH, and that should give me 0.112 moles of HCl. And again, this makes sense because the ratio between HCl and NaOH we determined from the equation is 1 to 1. All right, so the next step here, so we have found out the number of moles of HCl, but the question here, the unknown here, is asking you the volume of the HCl solution. Now again, it's the same idea. We know the concentration of the HCl solution, and we also know the number of HCl, the solute, number of moles of HCl, the number of moles of solute. So we should be able to calculate the volume by using the number of moles of HCl dividing by the molarity of HCl. So this is exactly what I did. I used 0.0112 moles divided by 0.556 mole per liters. Now you can also use dimensional analysis, of course, as stated here, and you should get the same answer, 20.2 milliliter. Okay, so don't forget about sig figs. I start with 3 sig figs in my question, and I should have 3 sig figs at the end of my question. So the conclusion here is we need 20.2 milliliter of HCl. So to summarize this video, what did you learn? Well, we learned that we need to treat mole ratio as the conversion factor that can allow you to jump to a different substance, either from product to reagent, reagent to product, reagent to reagent, product to product. So the key here is we learn many moles conversion factors, okay? So this is how stoichiometry questions can get tricky. Instead of me giving you something in number of moles, I could give you something in number of volumes of, like for example, a gas at STP, number of volume of, let's say, a solution, and give you the molarity as well. Or maybe I can give you the density of the compound, or even the number of compounds as well. But then the key step here that you need to understand is you basically just need to convert everything back to moles before you put your information into your BCA table. So this is essentially basically asking you to apply what you've learned in the moles unit.